Hello, you all. Daryl Lee Berry Jr. back with some Science Hour. Going to do some thermodynamics today. I just had a thermal exam on Wednesday and a quantum 2 exam on Friday. So I think I did all right on the thermal. On the quantum, it's a bit iffy, but the final will um, overwrite the lowest midterm grade. We had 2. So I'm confident I'll do really well in the final. So that's my strategy there. So we'll see how that goes. As a matter of fact, next week I'll do some quantum for this stream. Somebody requested more information on one of the things I talked about one week uh, in passing a little bit, and I talked about fields, subatomic particles and fields. So that'll come up in the final, I'm sure. And good to see Sean Hawkins. Thanks for being here. And he says you need to use your big brain and invent a UV activated resin that withstands 500 Celsius temps. You'd be rich. Okay? A UV activated resin that withstands 500 Celsius temps. What would that be used for? Like, what is that? What would that be used in or for? What kind of device? For 3D printers. Interesting. Thought about being an inventor. I mean, I have ideas for some inventions, but kind of hate like inventing building stuff. I think I'm more geared towards the theory side. And maybe that's part of the reason why I like the kind of research that I was doing in astronomy, where, satellites get the data and I just analyze the data and find out what's going on. Or if I, take my telescope and camera out, or even a big telescope and see things in the sky. Can't say I would enjoy building stuff. Right now, I'm actually taking a building scientific apparatus class. They allowed us to use that instead of advanced laboratory, and that fit with my schedule better. Well, I'm doing all right with it. I'll talk about the invention I made. I need to add that to the schedule. John says I can't invent, but I can modify and make a part better. Yeah, there's a lot of money in that. I often think about that, like when I see, like I saw a video on YouTube the other day where uh, in some country, I think Japan, like the uh, construction workers outside in the summertime, they have jackets that have a little fan on it, and then the fan is battery operated, so they can just turn it on and it circulates air inside the jacket to keep them cool. I thought that was pretty cool. So I think, why didn't I think of that? So I mean, so you can get rich inventing stuff. I guess I never really think about inventing things. Sean says I found an open source project that's a 3D printed tracker for cameras or telescopes. That that sounds nice. Seems like it'll save a lot of money. Um, yeah, all my stuff is like basic. Matter of fact, I have another solar filter, because the solar filter I use, which made my favorite picture of the sun. Um, the what do you call it? The grooves on the junction between the telescope and my camera stripped because the camera's so heavy. And so I bought a filter to put just directly on the camera. So I plan on taking a picture. There's actually a contest coming up soon. I need to check the date on that. There's another astronomy pictures by students here contest coming up. One of my son pictures is already featured. So I'm thinking about going out and taking a picture with this new filter. Let's see. Photo. Yeah. So it looks like the deadline for this is May 15th. So I have a lot of time. I need to put this on my calendar. I'll leave this email up. Before the 15th, I'll make sure to go get a picture with my new filter, and I'll show you all as well and see how it looks. It's awesome. Well, seeing you, Sean. Hopefully you enjoy today's topic. Let me know if you have any questions. I'll be talking about Boltzmann statistics. And this is the textbook, by the way, the textbook that we're using in class, and what do I have maximized as covering the, I think the Discord broke. Hold up here, see what's going on. So what is blocking Discord? I have some window up that's blocking Discord. Let's see. It's not that, not this, not that. All right, I don't know what it is. I'll just end the share and start the share again. See what happens. Share. Try this again. Hmm. So something, for some reason, is blocking the Discord. I don't know what it is. Hmm. Oh, I see what it is. There we go. Fixed. I clicked I forgot to open up the chat, is what it was. All right, there we go. So this is the textbook that we're using in this class. Here's an image of it. I actually think it's a good textbook. I can't say I generally like textbooks. Sometimes it seems like they're written to confuse you, like it's written just so the person who wrote it can be like, oh, look how smart I am, rather than actually writing to teach. So this seems like a book, a textbook that's actually written to teach physics, like it's written for you to actually understand what's going on, not just to. And one interesting, I guess I should say, not interesting, but one common feature of these textbooks that's written like as if it's like just a flex for the author. All throughout the book, they don't explain stuff. They just call everything trivial. Like they'll start some kind of calculation and be like, okay, well, I won't do the rest because that's trivial. It's like, what the hell? I don't know. I have no idea what you're doing. It seems like the purpose of the book is to explain what you're doing. And they just like stop halfway or less. And like, oh, well, it's trivial. I won't keep going. And that's when it seems like they're just like showing off. But this book, thinking about it, I don't never once remembering this author saying anything like, you know, it's trivial or I'm not going to do this. Sometimes they say, you could calculate this on the homework, but it's always when they've already done something similar or like show an example. And they're like, okay, there's another example like this thing here is different. And that's in homework problem number, whatever. So it's a pretty good book. So what I'll do is go through some of the theory on my other channel. I actually calculated some earlier problems. So I'll go straight to uh, the section 6.2 problems and show you all that one. So first I'll talk about what this is. So the idea is that Boltzmann statistics are, uh, in a sense, a way to deal with more complicated probabilistic things. So those who've been following along, we've spoken about entropy a few times. Entropy is a big part of thermodynamics. And so when you talk about entropy, you're talking about this is like the basic entropy equation, S standing for entropy, the Boltzmann constant times the natural log of the multiplicity of a system. So the multiplicity is going to be how many different ways that system can have the same energy. So the more ways a system can have a certain energy, uh, the more disordered it'll end up being. Similar to how if you're on the beach, sand gets everywhere, right? Something like that. So the idea is that if you have a system, the multiplicity that has the greatest number of components to it will be the most likely. That's what entropy is talking about. So if I have a system where there's 10 ways to have one state, but there's only 2 ways to have another state, because this has 10 ways to get that energy, it'll be most likely if the state is in equilibrium, and that's a key point. If the state is in equilibrium, so that every state is equally accessible, then of course the the energy state that has more options or ways to reach that energy will be hit more often because there's a whole lot more of them, right? So the idea that the universe tends towards states of high entropy means it just tends towards states where there's a higher probability of that state to be reached because there's more options for that energy state. Now, when you're dealing with things like what we've spoken of before, like we did things like an Einstein solid so many weeks ago, where you have a solid that's modeled as if you have a bunch of oscillators. So you have these little oscillators, which are the subatomic particles, and all these oscillators are vibrating, and they're all extremely similar. Basically, they're indistinguishable, and each of these oscillators are treated as a a particle, so many particles that can have so much energy, and there's a multiplicity function that deals with that, or dealing with the paramagnet. We talked about a paramagnet a bit, where you have, a series of particles that can be magnetized in a magnetic field. So, and they can either be up or down, for or against the magnetic field. So the magnetic field is going this way, then the one that's pointing up will have to have more energy because it's going against the field, and the one that's pointing down will have less energy. And for instance, each of these particles have 2 ways to point. So you can say the multiplicity of this whole system will be 2 to the n, in this case, which is 2 to the 5 ways that this system can configure itself. Um, so one case can be if all of them is down, if all of them are down, so you have, so let's just call n up equals 0 and down equals 5. Well, there's only one way to do that one, right? But you can have n up equals 1 and n down equals 4. But any of these ones can be up and all other 4 down. So it looks to be 5 ways to do that one. So easy way to do this one is you have the multiplicity would be 5 choose 1, it should be. So we have 5 factorial over 4 factorial, 1 factorial. So that's 5 divided by 1, which I intuitively saw it should be 5. You can have all of them down except this one up, this one up, this one up, this one up, this one up. So there's 5 ways to have that. And if you add up all the ways, so when we get to the states where there's 2 or 3 up, then there's a whole lot more ways to do that, and so on and so forth. And 2 to the 5 is what? 32. So if you add up all these different ways, should be 32 different ways to maneuver these particles, how they're pointing. But these are pretty simple. But when you get into more complicated systems, like what they're talking about in chapter 6, you have basically a reservoir, which we've spoken about before. So you have a reservoir at a certain temperature. And now instead of, let's say, this Einstein solid or paramagnet or whatever being separate on its own, isolated, now you have the system connected to a reservoir. And now the multiplicity, instead of it being related only to, oh, hold up, this again. So they may happen periodically. That's something new. When I'm watching the screen, and if I miss it, let me know if that goes crazy again or something and I miss it. So you have a system, whether it be a paramagnet or whatever, or an atom, it is connected, or we recognize it's connected to an outer system like the atmosphere. Then now the multiplicity will be related to both of these things together. You can't just take one on its own. And now it's not so easy just to do like a twos um, thing. So this is like the multiplicity of uh, n up equals 1, for instance. Hey, what's going on, Catherine? Awesome. Thank you. I appreciate it. And thanks for coming to the stream earlier. I'll make sure to each one do a different topic, like move to a different section, so you can go to either one and you'll always get something new. And that'll motivate me to not get lazy as well. I'll just study this one part because I got to actually get through this whole chapter and chapter 7, like in the next 2 weeks. Like 2 weeks. 'Cause like I said in the earlier stream, I've been sort of behind focusing on that exam, but the final is coming up. So I'm in crunch time. So I got to keep going. So thanks for showing up for both, and I'll keep on making sure each one I teach upon something different. So we'll go into the theory on this one, and then we'll go straight to the 6.2 problems. And I may even be here tomorrow to do more, actually work tonight. So I'm sure I have to get some sleep at some point. So, but the idea will be to get through chapter 6 over the next few days, and then move to chapter 7. So that's what we're looking at. So we have this system, and we have uh, a reservoir that is connected to. So we have the reservoir at temperature T. The reservoir itself will have a certain energy. We'll see this, the energy of the reservoir, and then the system will have its energy E, and energy can go back and forth between these two, and that will determine the multiplicity of the entire system, how these two change back and forth. So this is the necessary background for the problems in section 6.2. So if we look at this, we have the reservoir and be, let's say, in system in state 1. So let's say if I called this state 1 and this state 2, it's going to be some state of the system. This state only 0 is up, this state 1 is up, but again, it could be no matter what we're talking about. So if I say this would be the multiplicity of the reservoir when whatever the system is, let's say it is an atom, is in state 1, and you will have the multiplicity of the reservoir when the atom is in state 2. And we'll use this to derive the equation we'll utilize later. And a reservoir, which I had to look up myself earlier, is basically anything that is large enough to where if energy is added to it, the temperature doesn't change. So with the atmosphere, for instance, you're driving around in your car, the temperature doesn't necessarily start going up 2, 3, 4 degrees just because you're driving around. The atmosphere is so big that when we add heat into it, the temperature doesn't change. When we add energy into it, so that's considered a reservoir. Right. So the idea would be that the probability, like here, we can take the full number of states going back to the paramagnet, and if I wanted the probability of getting the nth state, it'll be 5 out of 32 because there's 5 ways to get uh, n up equals 1, and there's 32 total states, so the probability of n up equals 1 is that, right? So that's the probability of n up equals 1. Just how many of them overall have n up equals 1, and then the total number of possible states you can have with that number of uh, items or particles or whatever you're dealing with. And the way this is related when you're dealing with a more complicated system is the probability of any state 2 relative to the probability of any state 1 is going to be equal to the multiplicity of the reservoir when the particle is in state 1 divided by the multiplicity of the reservoir, assuming when the system is in state, I mixed up my 1 and 2. This is 2, right? So the probability of the system being in state 2 relative to the probability of the system being in state 1 is equal to the multiplicity of the reservoir when the system is in state 2 divided by the multiplicity of the reservoir when the system is in state 1. Because the multiplicity of, let's say, the atmosphere is, it's very complicated. So we don't generally try to calculate those things individually. I don't know if it's even possible. We can calculate relative probabilities even though you're dealing with this large system. And that's a good question, Catherine. Yes. So basically the idea would be, and this is an important concept, if you have a paramagnet with 5 particles, so that makes n equals 1, let's say, it's 5, let's say. That means that this paramagnet, if it's a paramagnet, that means that each particle could either be up or down. It can have 32 total states altogether, 32 total states. Because you can have one where all of them are up. You can have one where all of them are down. You can have 5 where only one is up, like we did earlier. You should be able to have 5 where only one is down. Right, so that's 10 together, and this is 12. You can see how they add up. And then when you start to do more and more, it starts to add up. Now, this is where I know the numpties call them. They like to throw around words like microstate and macrostate without having any idea what they are. But this is what it really means. So let's say you can have a paramagnet where only one is going up. Well, we could do the calculation. So let's do the in choose things. So the way it works is NQ is n factorial uh, over uh, Q factorial and n minus Q factorial. This is how you can get the multiplicity of the state. So if you have 5 and 0 are up, means all of them are up, that's going to be 5 factorial over 0 factorial, 5 factorial, which is going to be 1 over 0 factorial, which equals 1. And of course, we know there's only one way for all of them to be up. 5 choose 1, so only one of them are up. It's going to be 5 factorial over 1 factorial, 4 factorial. So that's 5 factorial. At least you could say 5 times 4 factorial over 1 times 4 factorial, 5. So that means that the macro state where where all of them are up, let's say 5 up, has one macro state, and the macro state where 1 is up, I'll just do it based upon the up. The macro state where 0 is up. It still be the same. The macro state where 1 is up has a multiplicity of 5 because there's 5 ways to have a macro state where 1 is up. Let's see. So we have 5, 2 up. So we have 5 factorial over 2 factorial, 3 factorial. So that's going to be 5 times 4 times 3 factorial over 2 times 3 factorial. So that's actually 20 divided by 2. So that's actually 10. So it actually goes to 10. So that means that the macro state where you have 2 up is going to have 10 microstates. And let's see if it adds up. Let's add them all up. So you can have 3 up. So 5 with 3 up. So this is going to be 5 factorial over 3 factorial, 2 factorial. So we can see that's actually the same thing as before. So we know that's going to be 10. So the macro state where you have 3 up also has 10 microstates. So in other words, the macro state is the overall state of the system, and the microstate is the specific way that system could be in that state. So you can have 3 up like this, but you can also have 3 up like this, right? These are the ones that's up. Oh, I miswrote 1. There we go. So these 3 are up there. These 3 are up there. So this is one microstate of the overall macrostate of 3 being up. This is another microstate of the overall macrostate of 3 being up. Ah, yes. It actually helps. And I actually did this to help me understand it. So it really helps to actually add them up and you can see how it fits. So let's finish. So we have 5 with 4 up. So it's going to be 5 factorial over 4 factorial, 1 factorial. And we can see that's the same as the one up there. So we know that's going to be 5. So the macro state with 4 up is going to have 5 microstates. Make sure I'm writing everything properly. 5, 10, 10. Oh yeah, that's right. That's a copy of that. Make sure I write that. So you can add these up. So the last one is going to be if you have 5 particles and all 5 are up. And we know what that one is already, but let's do it just in case. That's 5 factorial, uh, 0 factorial, 5 factorial. So that's 1 divided by 0 factorial. So that's going to be 1. So the macro state where all 5 were up is going to have 1 microstate. So let's add these up. I have 1, 6, 16, 26, 26, 31, 32. So there's 32 total microstates for a system with 5 paramagnets, and that's what we had at first, right? Just by looking at the fact that each paramagnet is going to have 2 states. So each one, 2 of them to the 5, so 2 to the 5, 32. So you can see how it all adds up. You can count all the microstates manually, and you see that there's 32 microstates. Or you can just look at the possibilities for the 5 paramagnets and see it's going to be 2 to the 5, which is 32 microstates. So it adds up. And so there you go. So now you have an understanding of macrostates, and how that's added up with a system of 5 paramagnets. And of course, it can get pretty complicated if you have a whole lot of paramagnets. We had only use 5. Make it not too hard. All right, so there we go. So now, keeping that in mind, when we go to this formula, we can understand what we're thinking about with the multiplicity, right, of the system being in a certain state, just like how the multiplicity of the system being in 3 paramagnets up is 10. This is what it's talking about. But this system is extremely complicated because now you have the atom atmosphere, and how many atoms are in the atmosphere. Like, I don't know, there's a whole lot, right? So it's going to be 2 to the a whole lot. It's going to be more than our calculators can handle. So that's why we start using a ratio to calculate these things. Now, we wanted to input entropy. We did the entropy equation earlier. So we have entropy is K ln, the multiplicity, in this case, R of Si. So we can actually divide both sides by K. And now we have ln R Si. And I can exponentiate both sides. And so now we know that the multiplicity, which is what we had here, I'll just copy this down and I use I to refer to any state. We know the multiplicity of any state can also be written as an exponential of the entropy divided by the Boltzmann constant. And Catherine says, that's amazing, Daryl. Thank you. I need to scrub up on doing factorials. Yes, factorials are fun. And for any watching who's not clear, I see we have a few watching. Be sure to drop a line if you like. So we have n factorial. That's going to equal n times n minus 1 times n minus 2 all the way into times 1. So that's all a factorial is. You just keep multiplying times the thing and then the thing minus 1 until you get to 1. And then when you get to 1, you just stop. And 0 factorial is equal to 1, which may seem odd, but that's the way that goes. 0 factorial equals 1. I think at one point I looked at some kind of proof of that, but it was so long ago and it was like ugly, probably, because I didn't even bother to remember it. Just know that 0 factorial is equal to 1, and then you're good. But now I'm curious how that's the case. I don't know. But whoever invented factorials, they knew that was the case. Otherwise, yeah, it'd be craziness, I guess. I don't know. But factorials are valid because they, we can calculate like we're doing now, we can calculate the states of subatomic particles statistically using factorials. So we know that somehow nature understands factorials, I guess is an odd way to say it, but all of these things relate to measurable quantities and they prove accurate because we have, oh, and I need to change my background. Oh my gosh. I did not put up the thermostats. Let me see here. I was about to refer to the thermostats, but the thermostats ain't up. Can't do that. There we go. All right. So now we have a proper thermodynamics background. So we know these things work because we have things like power plants and so forth that works on these things. So, all right. So now we have a stand-in for the multiplicity. So we can say this equals E, uh, the entropy. Let me make sure I write my subscripts properly. I hate subscripts sometimes. So we have the entropy of the reservoir when the system is in state 2 divided by K divided by the exponential of the entropy of the reservoir when the system is in state 1 divided by K. So all I did was uh, plug this in to here using the specific, what do you call it, multiplicity that we're talking about. All right. So let's simplify this. So this same ratio is equal to E exponential. And now we have the entropy of the state when the system is in state 2 minus the entropy of the reservoir when the system is in state 1 divided by the Boltzmann constant. And we can utilize a thermodynamics identity, which is a whole nother topic, but suffices to say that uh, if you have a uh, entropy of a system, I you can actually relate that to the energy of the system divided by T, right? So, but that's another topic. Maybe I could do that another day. With a thermodynamic identity, basically, these are like if you measure the volume of a system with a given number of particles and a given energy, and divide that by temperature, you can see how it relates to the entropy of the system. And if we keep certain things constant, like in our system, we have a certain number of particles, like a certain number of paramagnets that doesn't change. We have a certain energy. Uh, 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 the energy doesn't change overall, and so on and so forth. This simplifies in this way. So what we can do then is we can substitute this in, and we can say this becomes E to the and maybe I should do some of this uh, derivation. So let me actually do a bit of this right here. I don't want to skip too much. So we have S R S1, or I should say 2 minus S R S1 equals 1 over T U R S2 minus U R S1 from the thermodynamics identity. And what we can do as well, we can say that uh, the energy, and let me see if I don't skip too many steps. Let me just write the thermodynamics identity real fast so this part can make sense. So the full thermodynamic identity would be 1 over T. Mu is like it refers to the chemical equilibrium. When you have a certain number of particles, you're going to subtract du, which is the change in energy, and we're going to subtract pressure times the volume of the system. So this is basically the relating entropy to the temperature of the system, the amount of particles in the system, the energy of the system, and the pressure and volume of the system. Again, this is a whole complicated thing to derive. Uh, and probably do that one week, but it's long. I want to make sure that we get to the thermodynamics problem. So I'll just throw this out as something just to know. Is actually related to equation 6.3 in the book there. So what we can do is if I actually substitute energy for this, you see that there's a negative sign there. So we can say, still skipping some steps, we can say SR2 minus SRS1 equals negative 1 over T, the energy of the system. So basically we could consider this E in this case. Like technically U is like how it's written by default, but we're calling the energy of our system E and the energy of the reservoir U. So since I'm going to substitute the energy of the system, I'm going to put the negative there since the negative is there. And this is where this negative comes up in the front right here. So we have ES2 minus ES1. And now I can substitute this in. So all of this is in the side. So continuing from this line here, we can say that the probability of the system being in state 2 divided by the probability of the system being in state 1 is going to be the exponential of negative E S2 minus E S1. And it was already divided by K, so now it's divided by KT. And we can actually separate these and say e to the negative E S2 over KT times e to the positive uh, E S1 over KT. And then we can go ahead and move one of those to the denominator and say e to the S2 over KT divided by e to the negative, e to the negative E S1 over KT. And now we have something relating the probability to the energy of the system. And ultimately, this is what we're going to use coming up. And this term here is called the Boltzmann factor. Hey, what's going on, Santosh? Good to see you. Let me know if you have any questions. Doing good, preparing for my thermal final, which I feel like I have to do good on. So this is going to be a prominent factor, unintended, I guess, of the grade because this is going to be a major part of the exam. One other detail, if I was to solve for, let's say, PS2, this will be this, and I'll just copy this to save some time, times PS1, just multiplying that over. And we can say that this is 1 over Z times e to the negative E S2 divided by KT. So that means that this term here is 1 over Z. And this Z is called I don't remember the name myself. Let me scroll and pick up the name. It is called the Boltzmann. Oh, some of our Boltzmann factors. I don't remember the name of this thing. I'm about to pull up the textbook as well. So let me pull up the textbook and we can look together and remind myself what the name of this thing is. Let me take the cover off and pull up the actual book. Is the book ready to show? Looks like it is. Boom. So let's see what this name of this thing is, because I forgot. So next section, the page down button. Partition function. Oh my gosh. Start the partition function. So the Z is called the partition function. All right. So now we have everything we need to answer one of these problems in section 6.2. So we're at the promised land, Catherine. We're here now. So the one I wanted to show y'all that I thought was pretty interesting is this one. So that is about atoms. It ends up being about the state of helium in the sun. So let me see if I can find the proper one. 6 point. It's problem 6 point. Well, not in the sun. No, I'm thinking about a different one. The previous one is about the sun. Actually, from a different. Okay, so y'all can let me know. Do y'all want to see the one about uh, hydrogen atoms in a star versus at room temperature, or the one about a water molecule vibrating in a 300 Kelvin environment versus a 700 Kelvin environment. So which one? Which one would y'all like to see? It's either 6.6 or 6.10. 6.10 is the main one that uses the partition function, by the way. Y'all gonna let me know. And let me, so this is 6.10 right here. The water molecule and how it vibrates. And this is 6.6. And are these, and one is in 6.1, and technically only this one is in 6.2. So the 6.10 is the 6.10 one is the 6.2 part. There we go. Or is it the 6.1? I don't remember. But there's no taker, so why don't I use this one? Because I thought this one was pretty interesting. Even though it doesn't deal with the sun, y'all know I like stars. All right. So it says, so this is 6.10. It says a water molecule can vibrate in various ways. So again, we have a H2O. So you have a oxygen molecule, and we have a hydrogen, and we have a hydrogen. If I remember right, this is pretty much how the molecule is structured. Like it's actually making sort of like a triangle type deal, if I remember right. And what they're saying is you have a vibration this way and a vibration this way, so that this length changes, but this area here does not vibrate, it stays the same. All right, so this is the kind of particle that we're dealing with, right? So it's saying that a water molecule can vibrate in various ways, but the easiest type of vibration is the cyclic flexing mode, which I wrote there. The oscillations of this mode have a frequency of 4.8 times 10 to the 13 hertz. And like a quantum harmonic oscillator, it has the energy levels of 1 over 2 HF, 3 over 2 HF, 5 over 2 HF. No, I believe they do. They do stretch. So there's this would be considered a diatomic molecule. So if all the different modes are active, it should be like 7 different degrees of freedom. So it should have this way back and forth. It should have this one vibrating. It can move back and forth. Like it should be like at least 7. In my formula sheet, I actually have the number, but yes, they can vibrate. Um, so no, it's not saying that. So when it says it can vibrate in various ways, this first line, that's what it's talking about. One of the various ways is the H and the O stretching. It's just saying the easiest is the flex mode, because there's not like a normal force or whatever holding those two together. You could vibrate without pushing against anything really, sort of free vibrating. Oh, you're welcome. So that's the purpose. So yeah, make sure to ask any questions. And that's one reason why I like doing it live, so I can have some questions to respond to and so on and so forth. So keep them coming. So that's how that works. In my chemistry class, actually, the chemistry class was legit. We actually had to I don't remember it now, of course, but we had to actually understand and calculate the angles, the exact angles of all of these things, because you have a hydrogen atom, and it has like 1 proton and 1 electron, and then you have the oxygen. It has like 16. It has a 16 mass, so I guess it has like 8 protons and 8 neutrons, and like we have to calculate. We have to do all of that and calculate the actual angle of this thing. And the different molecules, they structure themselves differently according to that. Because if you have a molecule that's structured like this, let's say, depending on electrons and how they repel, this angle will be different, and this angle is just, it's pretty complicated. With all the chemists, they know exactly how these elements look, and because and you can calculate it quite precisely when you understand the way the electrons configure themselves and how many electrons does it have on the outer shell. It just gets complicated, right? I mean, I learned it briefly to pass the test and everything, but I knew I wasn't going into chemistry, so I didn't like learn it to memorize it forever. So in says I remember doing that, but I didn't know they could sketch. It's fun though. Yes, I think it is kind of fun. Yes, I enjoyed that class. They made that chemistry class fun. I did briefly think about going into chemistry because of that class, how fun it was. And what I'll do is do the first one with the 300K, and the second one is pretty easy. So it wants us to calculate the probability of the water molecule being in its flexing ground state and in each of the first two excited states. All right, so this will be easy enough. So we could use everything we learned earlier, which is why I want to cover that. So we know Z is going to be the sum, and maybe I didn't specify that. So we did the Z for one different state, but to get Z of a more complicated thing is going to be the sum of all the different E's. So in this case, the Z was just the one E, because we only have the one other state. I utilize a simplified system. But if you have a more complicated system, like if I did the full 5 paramagnetic thing, you have to add up each of the E's for each of those entities of each of those systems. So it ends up looking like this. So I'll just call it I E of the negative E I divided by KT. So if I wanted the Z here, it'll be E to the negative HF over 2 divided by KT plus E, this is the 3 right here, to the negative 3 HF over 2 divided by KT plus, and so on and so forth. But I can tell you that this gets very small, so I'll ignore that one. Now, and I did the math on this earlier, so I could just type out the numbers for you. And the way I did this was I multiplied what HF is. So HF is going to be the Planck constant, and the frequency is the frequency that we had earlier in hertz. The Planck constant is 6.626 times 10 to the negative 34 joules times seconds, and hertz is 1 over seconds. So when I multiply that in, HF is 3.18 times 10 to the negative 20 joules. So that's that. And KT for T is 300. The K is the Boltzmann constant. So that's a constant that's inherent in nature. In my modern physics lab, you can actually measure it. I didn't choose to do that experiment. I'll take their word for it. I wanted to measure the speed of light, but there's people that measure it pretty regularly. And we're using the temperature of 300 K. So this combination equals 4.14 times 10 to the negative 21 joules. All right. So when I plug this in, Z is going to equal E to the negative 3.18 times 10 to the negative 20 over 4.14 times 10 to the negative 21. And it's still a 1/2 there, plus E to the negative, and you notice there's a 3 on that one. So 3 times 3.18 times n to the negative 20 over 4.14 times 10 to the negative 21. And there's still a 1/2. And there's a whole bunch of one of those I'm ignoring because they're so small. So the values I got for this were 0.21 plus 9.895 times 10 to the negative 6 plus something very small, and it equals 0.0215, and that equals z. So that's the, what was it, partition function? Partition function, yes. Remember the names for these things. So now we have z. And again, we're trying to get what we need to get this probability. And we're going to get the ratio of these probabilities. No, it actually wants the specific probability. It doesn't want the ratio, so we can actually get the probability. So we got the z, and now we can get what we need because we know z. So the probability is this. The probability here of SI, I'll just make it generic, is this. All right. So I'll copy this down. So the probability of the state in state 1 is going to be 1 divided by 0.0215 e. Now I've already calculated this exponent here, right? You see I've already calculated that. So instead of calculating it again, I'll just plug it in here, 0.21. So that probability is 0.98. And the probability of state 2 of the system being have in state 2 at the given temperature is going to be this same thing here times this one, and that's going to end up being 4.6 times 10 to the negative 4. So it gets very small. So that means that at room temperature, and let's look at the question again. You wanted to know the probability of the water of this vibration happening at the first or the second energy level. Like, is it vibrating with just normal energy or vibrating with a whole lot of energy at room temperature? It's vibrating normal, which is to be expected, right? And if we did the same thing with the temperature at 700 K, process would be the same, except the KT here, what did I do, KT? Here, it'll be KT for 700. So KT 700, if I plug those numbers in, it ended up being 9.667 times 10 to the negative 21 joules. And then we got to get a new Z, because it's going to be Z equals E. Everything else is going to be the same, except now I'm going to have to divide by KT 700. And when I plug those numbers in, I end up with 0.197 plus 0.007, which equals just about 0.2, right? Just about 0.2. So when I plug those numbers in, so now we have the same water molecule. Now we're trying to see if we turn the temperature up to 700 degrees Kelvin, how does just that one vibration react, that one vibration in the sort of wiggle part react. So for the lowest energy state, we have 1 divided by 0.2 times 0. And this was for, did I scroll properly? Oh, I think I rewrote the wrong thing. Hold up here. Let's see here. KT7, 0.19. Oh, I added an extra 0. Okay, let me do it. I'm good with doing that. Adding extra zeros. See if I changed anything else around. Oh, and this was actually a 3. Right, or what a 7 there by mistake. There we go. There we go. Okay, that looks right. There we go. So copying everything down. I noticed when I was copying it back down that, hold up, that's not the right number. So it ends up with this, and this ended up with 0.965, and the probability of the second state 1 over 0.2 times 0.007. This ended up being actually 0.036. So this means that at low temperature, room temperature, we have the large majority of them are not vibrating very fast in that way. The amount that's vibrating in the excited state, the first excited state, is really negligible. But if we turn the temperature up to 700 degrees Kelvin, we see that it drops down a bit, noticeably enough, and a lot more are vibrating in the first excited state, right? When we get up to the sun and stuff like that, it starts to get very big. The Catherine says 4.8 times 10 to the power of 13, though, that frequency incredible. Ah, yes, the frequency here. Yeah. So these things are, because, I mean, things are so small. Um, so I could look up the size of them, but yes, these things, it's crazy all the stuff that's happening. As a matter of fact, you can kind of see it. Like there's an experiment in the modern lab, um, the Brownian motion experiment. And what you do is you get these little bitty spheres. I mean, they're these like nano-sized spheres, and like there's a whole bunch of them, like a lot of them, and you put them in a solution of water or something like that. And there's a microscope that's zooming in on it, and you put it inside. We watched TV before. You know how you can take these things and put on a little glass slide and put under a microscope. So you imagine these things very small, and compare it to the microscope, to the little slab that the glass thing, and there's a little bump in the slab that you fit it in, right? And you put this under the microscope, and then when you zoom in, you can see these little particles vibrating and moving. And the purpose of that experiment is you can actually calculate, you can prove that Brownian motion is a thing. And I think you could even calculate one of the constants. I don't remember what constant. That was not my forte as well. I mean, I'm familiar with it because I helped the students in it as a learning assistant in the labs. I looked it up and got familiar with it, but I didn't actually do it when I was in the class. So there's still some details I don't know about it. But suffice it to say, you can look at it and see these vibrations and how it's faster than we can notice with our eyes, but you can see these things are moving very, very quickly. It's very clear to see. So, and it's kind of, we can see it to an extent. Like if you ever look at like a rabbit eat or something small eat or a squirrel, you can see how fast they might move. Everything is fast. When they look side to side, their movements are so fast, but they're so small. But it seems to be amplified the smaller and smaller we go. All right, so y'all got some Boltzmann statistics today. Nice overview of the theory. Calculated a later problem. Um, Smoke in the air is an example of Brownian motion too. Yes, I believe so. Anything that's dropped, any uh, particulate that's dropped into a reservoir of something else, blood in the ocean, it should all move with Brownian motion. So it's pretty cool. Yeah, so good catch. So awesome. Hope you all enjoyed at the top of the hour. I think that was a good science hour. Pretty good overview. And I'll be trying to do more on my other channel as well. So I would say if you want a more in-depth, like Catherine was there earlier, where I actually go step by step, pretty much on my other channel, like work the problem for the first time and actually work through it. And here I sort of give an overview so you can get an overview of what's going on. If somebody asked a question like Catherine had asked about the multiplicities of this product of this paramagnet, and we worked that out in detail. So we do some things here. But I would say if you want a more in-depth, the STEM channel, a more overview here, and I think both of them are important, right? On one hand, you can look at more in-depth on this one thing, but also the overview helps you get a better picture of things. So I think both of them are important. So that's right why I have both channels. Hopefully to see you all on both. Make sure to keep progressing so each channel sees something slightly different. One thing I added, by the way, I don't see the mathematician this week, but if anybody wanted like a problem work through, I've also added a problem walkthrough on my Patreon. So if somebody wanted to get a problem walkthrough, if you're in school or something, you can join my Patreon and I can actually devote an entire science hour to working your problem and explaining it. So you should welcome, Patrick. Thanks for being here. Thanks for showing up. Thanks for communicating. It was good seeing Santosh and who else was here? Sean Hawkins. I could have swore I saw somebody else here earlier as well. Maybe it was just one of the numbers that popped up. So I'll see y'all tomorrow. If anybody want to show for metaphysical hour, and I'll be next week to talk about quantum mechanics. That was brought up earlier about having a particle in an electric field, so you don't want to miss that one. I'll refresh myself on that, which I need to do for the final anyway. So I'll refresh myself on that, and we'll talk about putting a subatomic particle in a magnetic field and see how that changes it. And good times. I'll see y'all next week.